This is the first of two videos that have to do with statistical inference. In this first one, I'm just going to cover sort of the basic idea about why we do inference and why it works, or how it works. And the second one, I'll go over a variety of inferential methods, actually quite a large variety in a very short period of time, hopefully. So, to begin things, let's start with what is a concrete example of where this might come into play. I just looked up what the average household income is in Iowa, and it's $68,446. I also had some data from each zip code. The 68,446 is the actual figure. It's from IRS, actually based on tax return data. The second data point here for zip code 52001 is actually based on a sample of information. There's something called the American Community Survey, and they report incomes by zip code, and the IRS eventually will report the actual data by zip code, but it's about a 2 or 3 year lag before they report it. So according to the American Community Survey, which sampled 168 households in the zip code 52001, the average income was $80,788. The question about statistical inference is whether we need to know any more or do we just stop there. 68,446 is clearly less than 80,788, but the 80,788 is only based on 168 households, and that's actually out of 5,603 households that are in zip code 52001. So it's only something on the order of 3% of the households that this 80,788 comes from. I'll also tell you that we know that if you look at the income of household income for those 168 households, the standard deviation, a measure of how much it varies from one household to the next, is 29,600. So in fact, there's quite a variety of incomes among those 168 households. So the basic question of statistical inference is, from this information, what can we actually say about zip code 52001? We have a point estimate. If we had to give a single number, the only number we have is 80,788. But can we say more about the range of incomes that might be plausible for zip code 52001 from this information? And maybe more to the point, can we, with some reasonable degree of assurance, say that 52001 has above average income for the state? Now, just looking at it, I think many people just jump to the conclusion that it is a relatively rich zip code because, look, 80,000 is quite a bit higher than 68,000. But we should want to examine this a little further because, in fact, we're only looking at 3% of the households, and there's a lot of variation among the 168 households that we actually have data on. In this case, I think, well, we can say that this is based on a random sample because the American Community Survey actually does random sampling. So a key question would be, what do we know about the 168 households that we have? Are they randomly selected? Are they ones that volunteered? If they volunteered, it's no longer a random sample because some people volunteer and some don't, and there might be some real difference. In fact, my guess would be higher income households would not want to volunteer as readily as low income households might, especially if there's any kind of reward for participating. But in any case, let's leave that aside and just assume that they are randomly selected households. Now, I will come back to this example after I go over some preliminaries here. And the preliminaries have to do with sort of the reason why we can say anything under these circumstances. And what I have here is a jump table that I created, which looks pretty uninteresting at this point because it seems to only have 6 column headings and no data in it. but I'll fill it with data here in a moment. If you want to see the formulas behind these columns, n equals 1, what did I do? I said, let's take a random normal distribution, take a random number drawn at that, and I'm only taking one number, so most of this formula is superfluous. I'm going to divide by 1, so I'm going to get the same number, and I'm summing a bunch of random numbers, except I'm only taking one. So summing 1, I'm just getting one random number. What does the random normal distribution look like? It's a bell-shaped curve. It has a mean of 0. This is what's known as the standard normal. So it has a mean of 0 and a standard deviation of 1. Virtually 99.6% of the data will be within 3 standard deviations of 0. That would be from -3 to +3. 95% of the time will be within 2 standard deviations, -2 to +2. And about 66% of the time will be within 1 standard deviation. We'll get a number between -1 and +1. That's what this column is doing, just picking one random number out of that normal distribution. If you look at the n equals 2 column, it's the same basic formula, except I'm going to pick 2 numbers out of that distribution, and I'm going to divide by 2. So I'm getting the average of 2 random numbers out of that same bell-shaped curve. Here I'm pulling 9 random numbers out of that standard bell-shaped curve, and I'm averaging their values. And so on. 49, 100. When I get to 100, I'm picking 100 random numbers out of that same bell-shaped curve with a mean of 0 and a standard deviation of 1, and I'm dividing by 100. So let's put some data in this. Let's go ahead and add a row. Let's just add one row first. Mean of 0, standard deviation of 1, the one number I picked. It's showing up on mine, and if you do this on your computer, you'll come up with different numbers because they are random. My first number was 2.05. When I picked 2 numbers and averaged them, I got -0.21. When I picked 100 numbers and averaged them, I got -0.25. Nothing too interesting here, just collection of those results. Let's go ahead and add some more numbers. Let's add 99,999. So I have 100,000 rows. Now I got something to work with. Let's look at the distribution of what we have. Notice n equals 1. I pick one random number. I'm getting a bell-shaped curve here to turn your head sideways. Notice the mean, 0.001, is pretty close to 0. The standard deviation is pretty close to 1, 0.999. That's what I told the computer to start with, a bell-shaped curve with a mean of 0, standard deviation of 1. When I pick one number at random, and I did 100,000 of these, and I look at them, they look just like the distribution I started with. Notice if you go across, all of these have a nice bell-shaped curve. They all seem to be centered on 0. The one difference is, if you start looking at the scaling, you'll notice the scaling is not uniform. I'll make that uniform here in a second. What you notice is they look extremely similar going across. But if you look at the mean and the standard deviation, actually, let me do the uniform scaling first. Now when I do the uniform scaling, and probably if you do the hand, you can actually generate a few more bars in here. Just put the hand in the middle of these and sort of scroll out. Now you can see that while they're bell-shaped, they do seem to be collapsing. The range is getting smaller and smaller. And that's verified when you look at the mean and standard deviation. The means actually stay pretty close to 0. They're random, so it's a little bit different. This one's a negative mean, but 0.0006. This one's negative, 0.001, still negative. The last one's positive, 0.0001 though. very small numbers. So the means are essentially very close to 0 all the way across the board. But look at the standard deviation. 1, essentially. Now it's 0.7, 0.71, 0.33, 0.2, 0.14, 0.1, getting smaller and smaller. That matches the picture where the distribution is getting narrower and narrower. There's actually a formula that this follows. This is what's known as the central limit theorem, and it says that as the sample size gets large, the sampling distribution for the sample mean, which is what we're looking at here. When you look at the mean of a sample and you look at how it's distributed, the mean of that sample approaches a normal distribution with a mean equal to the mean of the population, what you started with, which was the one on the left, mean equal to 0, and a standard deviation given by the standard deviation of the population, which was 1, divided by the square root of the sample size. When the sample size is 2, 1 divided by square root of 2 is 1.41. 1 divided by 1.41 is about 0.71. That's what we have here. Square root of 9 is 3. 1 divided by 3, 1/3. Standard deviation is 1/3. 1 divided by square root of 25 should be 0.2, 0.201. Square root of 49 is 7. 1/7 is about 1.14. Square root of 100 is 10. 1 divided by 10 should be 0.1, pretty close to 0.1. Looks like the central limit theorem is in fact what we're getting, what we're seeing demonstrated looking across this. The central limit theorem actually says a bit more than this, because I can modify these formulas. Instead of a random normal, suppose I put in a random uniform distribution. A random uniform distribution says everything is equally likely and you can give it a minimum and a maximum. If you don't put anything in, it'll assume it's from 0 to 1. So it's going to give us uniform numbers randomly somewhere between 0 and 1. Let me put that in. And I have to change all the others. Two left. Let's look at what we get. Remembering that sample size of 1 is basically the original distribution that all the samples are drawn out of. So the true distribution, if you like, looks a lot like what the sample size of 1 looks like. There's our uniform distribution. The fact that it's only 100,000 data points is why it's not perfectly even across, but it's pretty evenly spread out from 0 to 1. And notice that the mean is pretty close to 0.5. And the standard deviation is actually 0.288 approximately, a little less than 0.288. You can think of the standard deviation as sort of the average deviation from the mean. Now, if truly we had numbers evenly spaced from 0 to 1, the mean is 0.5, and the average distance from that 0.5 would be 0.25. The only reason why the standard deviation is larger than that is that the standard deviation is not really the average distance from the mean. It's the distance from the mean squared, adding that up and taking the square root. And so when you look at the formula for the standard deviation, it is larger than the average distance from the mean because we're squaring the distances, so distances far away count more. That's really a minor difference here. Basically, if you want to think of the standard deviation in intuitive terms, it is sort of means the average distance of each point from the mean. On the average, how far away from the mean are they? It's not exactly that mathematically because of the square term and then taking the square root, but 0.25 would have been exactly the average distance from the mean, but we get 0.288 here. Now notice with the sample size of 2, what happened to the shape? It suddenly became triangular. It's not bell-shaped, but it's not evenly spread out. The reason is if you're taking two numbers at random from that left-hand distribution, sometimes they'll both be above 0.5, sometimes they'll both be below 0.5, but a lot of the times you're going to get one that's above 0.5 and one that's below 0.5, which is going to start building it up in the middle. In order to get a value close to 1, which on the left-hand one happens as often as any other range, so if you look at the range of 0.95 or 0.975 to 1, that first bar up here, that happens about the same frequency of all the other ranges. But to get the average of two numbers to be in that same range, both of them would have to be in that range. That's not going to happen very often. So in fact, there's almost no chance of getting a value between 0.975 and 1 when you're taking a random sample of two numbers from the left-hand distribution and averaging them. On the other hand, you're more often going to get numbers around 0.5 than you did on the left. This probability is getting built up because there's a lot of ways you could get numbers near 0.5. You could get both numbers near 0.5. You can get a number as high as 1 and another number as low as 0, and they'll average to 0.5. So now there's a lot of ways this can happen. Notice when we get to n equals 9, it's actually starting to look bell-shaped. Looks extremely bell-shaped at 25, sample size 49, and sample size 100. Central limit theorem says on average the mean will approach the mean of the population. Was 0.5 essentially was the mean of the population. Notice, even with a sample size of 2, the average is 0.5. It's 0.5 all the way across. So the mean is pretty close to what the population mean is. What about the standard deviation? I said it's the standard deviation of the population divided by the square root of the sample size. Well, the sample size of 2 divided by 1.41, the square root of 1.41. Square root of no, it's divided by 1.41, the square root of 2. So we have 0.288 divided by 1.41. You can do it on a calculator. It's pretty close to 0.205. Take an easy one, divide by the square root of 25. That's 5. 0.288 divided by 5 is about 0.058 something. Yeah, 0.058, pretty close. Divided by 100, 0.288 divided by 10 would be 0.0288, 0.0289 here. So it looks extremely close to what the central limit theorem would say. So in fact, the central limit theorem actually holds for any shape of an original distribution. So again, the central limit theorem says as the sample size gets large, the sampling distribution of the sample mean approaches a normal distribution with a mean equal to the population mean and a standard deviation given by this population standard deviation divided by the square root of the sample size. And so the question would be, how large does the sample have to be? Rule of thumb usually is by the time n equals 30, sample size of 30, you can pretty much use the central limit theorem. I've actually seen exceptions to this. If the original distribution is highly skewed and really has a strong high peak somewhere called peakedness, then it's possible the sample size needs to be larger, maybe even larger than 100 or more. But for most uses, and pick up most books, it'll say a sample size of 30 is sufficient to rely on the central limit theorem. We started with a distribution here that didn't look at all like a normal distribution. And by the time we got to sample size 9, it starts looking bell-shaped. And even at sample size 2, the mean and the standard deviation are pretty close to what we'd expect from the central limit theorem, even though it doesn't look bell-shaped yet. So it doesn't take much of a sample in order to rely on the central limit theorem. The key caveat being it needs to be a random sample. If you have a non-random sample, all bets are off. There's actually nothing you can say without a lot more analysis about what happens in a non-random sample, because you're systematically biasing things since you didn't get a true random sample. But if you have a random sample, the central limit theorem is an extremely powerful way that you can analyze it. So let's return to see how we use this. Go back to my whiteboard. So here's our sample information. We had a mean of 80,788. We have a sample of 168 households. The standard deviation among those households is 29,600. According to the central limit theorem, we should be able to say something about the true mean of household incomes in zip code 52001. I'm going to use what I would call a 95% confidence interval. Centered on what we found in our sample, plus or minus. Now, here's where we need to rely on the central limit theorem. How far off could we be? Well, we already know the central limit theorem says that we should be the standard deviation for the sampling distribution, and that we have a sample mean here of 80,788. The standard deviation for the sampling distribution should be given by the standard deviation of the population divided by the square root of the sample size. So we could take the 29,600 divided by the square root of 168. Now, if you are following me, you should have, a question should have occurred to you about, well, is 29,600 the standard deviation of the population, meaning all households in zip code 52001? The answer is no, it's the standard deviation to the 168 households that we had data on. We're supposed to use the standard deviation for all the households in 52001. But of course, we don't know that. If we knew that, then we wouldn't be going through this exercise. We would just be, if we had data on all the households so we could calculate the standard deviation, we would also know what the true mean is for zip code 52001 because we'd have all the data. So all we have is the sample standard deviation, 29,600. I just applied the central limit theorem in this formula by putting in the sample standard deviation where the population standard deviation was supposed to go. And what I consider the most amazing result in statistics is the result that's attributed to a person named Student. I always thought it was an odd name. He actually worked for a brewery in the 1800s. And at that time, when you published work, it was often done on a pseudonym, and he chose the pseudonym Student. And what he discovered is the student t-distribution, which basically said, if you're using the sample standard deviation as an estimate for the population standard deviation, you cannot look at a standard normal distribution for the central limit theorem. You need to look at a t-distribution. And if you look at any book or a table, statistical table, at what a t-distribution looks like, the remarkable thing is the t-distribution looks exactly like the normal distribution. except that it's a little bit wider. Once the sample size gets as large as 30, there's almost no difference between the t-distribution and the standard normal. If your sample gets to 100, they will actually stop printing tables for the t-distribution because it's so close to the normal distribution, it's really the same thing. So if you can rely on the central limit theorem, meaning you have a random sample of at least 30, you can also rely on the t-distribution looking pretty much exactly like the standard normal distribution, just slightly wider. And to get 95% of the data in a normal distribution, you have to go actually 1.96 standard deviations on either side of the mean. 2 is a good rule of thumb. And since the t-distribution is actually a little wider than the standard normal, essentially you need to go 2 of these. So what I need to do is multiply this term by 2. So I'm taking the mean from the sample. I'm going to what's called standard errors, which is the standard deviation of the sampling distribution. 2 standard errors on either side in order to get 95% of the probability. The standard error itself is the standard deviation of the population, which we're using the standard deviation of the sample in place of it, divided by the square root of the sample size. When you do this calculation, it'll end up being approximately 76,218 to 85,354. So that's the approximate range for this 95% confidence interval. So what you would say from this is, by applying the central limit theorem, you would say, I will say it, although I'm going to tell you in a second it's wrong, but I still will stand by it, that I'm 95% sure that the true mean household income in zip code 52001 is somewhere in this interval, 76,218 to 85,354. And notice that 68,000 is definitely lower than that interval. So I would say I'm at least 95% sure that zip code 52001 has a higher average household income than the average for the state of Iowa. More than 95% sure, actually. Now, technically, that's not right. And if you look on a number of blogs, you will find statisticians get extremely upset at the fact that even many statisticians cannot correctly interpret a confidence interval. The correct interpretation of the confidence interval is that if we do this repeatedly, if we were to take random samples over and over again, 95% of the random samples that we take will lie within 2 standard deviations, standard errors of the sample mean. So we do this a whole bunch of times. 95% of the time, constructing an interval like this will contain the true mean. I have contributed to a number of those blogs saying, I frankly don't think this point is really worth making, because what we have is one sample. And the question is, what do we know about the one sample? The technically correct answer, based on one sample, we can't say anything about a confidence interval. The true mean either is inside that interval or it's not. It just is or isn't. The central limit theorem basically, and the true definition of this confidence interval says if you do repeated sampling, 95% of the time, you'll be within an interval constructed in this way. It's a property of the process of developing a confidence interval. But as a practical matter, my opinion is if you have one sample, you don't know which one it is. It may be one of those 95% that the true mean does lie within this interval, or the 5% that it doesn't. How would you assess the probability that the true mean is inside this interval I just constructed? I have to say is a 95% chance, because there's a 95% chance that this is one of those samples that the true mean is inside this interval as opposed to one of the 5% that is not inside this interval. And by the same logic, I would say I'm more than 95% sure that this particular zip code has a higher average household income than the average for the state as a whole. This point gets debated constantly on different blogs. Only some statisticians are purists that insist on saying that this is a wrong interpretation of confidence interval, but according to them, then you'd never be able to say anything on the basis of sample information unless you took repeated samples. So I think they're arguing about a theoretical point that has no particular consequence, and I feel pretty comfortable saying I'm 95% sure the true mean lies in this interval, even recognizing that I'm actually misspeaking about what the confidence interval tells me. Now, just to take it one step further, and this is the step that confuses people immensely in a basic statistics course. This will take at least a month to cover, and at the end of that month, half the class will basically be lost for the rest of the semester. You may identify with that from when you took statistics. And this is to turn this into a hypothesis testing example. I'm almost inclined to not cover hypothesis testing. There is a movement afoot to stop using hypothesis tests entirely. Andrew Gelman actually says he will not teach introductory statistics until we dispense and get rid of the whole idea of hypothesis testing. There are psychology journals, a couple of them have announced they will not publish articles that use either hypothesis testing or confidence intervals. I think they may be going overboard, but since hypothesis testing is so common and still used, and probably we will all be dead before it really disappears, I feel compelled to at least cover it minimally. So I will mention hypothesis testing, which essentially is what we've already done, except it turns the logic around. Instead of saying, what interval am I 95% sure, based on this sample information, that the population mean for the zip code is in that interval, the hypothesis test would say, can we be sure that this zip code has a higher average income or even a different average income than the state of Iowa as a whole? So it's only a sample information. So what we're going to do is we're going to state a hypothesis. And the thing that confuses people with hypothesis testing is you feel like you're apt to prove something, when in fact you're apt to disprove something. The hypothesis you set up is the opposite of what you're looking to be able to say. And you're seeking whether you have enough evidence to disprove that hypothesis. Let me bring up something else here. The best analogy for a hypothesis test is to look at a jury trial, because it's a very similar kind of situation. In a jury trial, you have somebody accused of a crime. Think of the trial as a hypothesis test. We're testing a hypothesis, and in fact, we're testing a very particular hypothesis. This person is not guilty until proven guilty beyond a reasonable doubt. So we set up a hypothesis that they're not guilty, and we say, do we have enough evidence to convict them? The trial hypothesis ends up with the result, either finding them not guilty or we find them guilty. There is truth here. They are either innocent or guilty, except we're not going to know the truth. There is no way we'll ever know the truth. There is no evidence that will tell you without any doubt at all what the truth is. You can have a video of a person committing a crime, and the video can be doctored. You can have eyewitnesses that are notorious for getting things wrong, remembering things differently than what they had. So in fact, we're not going to know what the truth is. But if the person is truly innocent and we find them not guilty, we've made a correct decision. That's this cell. If they are guilty and we find them guilty, we've also made a correct decision. But there are two errors we can make. We can find them guilty when they're truly innocent. That's known as a type 1 error. Or we can find them not guilty when they really are guilty, and that's known as a type 2 error. Generally speaking, errors are not symmetric. And depending on the circumstance, you might be much more concerned with one kind of error than another. And it's especially true in business applications. In a jury trial example, the Constitution actually tells us what the asymmetry between these errors looks like. The Constitution basically says the worst kind of thing you can do is to find somebody guilty that is not guilty. And this is why we say you have to be found, the evidence you have to be found to be guilty beyond a reasonable doubt. The idea is a pretty steep burden of proof to find somebody guilty, and that's why people get off on all kinds of conditions. And if you have a good lawyer, you can get off from crimes by using the law, the loopholes that are built into the law, and those loopholes are there for a reason, in order to protect against type 1 errors. Do we make type 2 errors? Lots of them. In fact, we still make lots of type 1 errors. That's really an unfortunate thing. As much as the Constitution tries to protect against it, we still make those kind of errors, but we make many type 2 errors. There are all kinds of guilty people walking around. O.J. Simpson is the one that I always think of, is if you're old enough to remember the O.J. Simpson murder trial. The jurors at the end of that trial said that they thought he was guilty. They found him not guilty. And that's because the judge did his job correctly. He had told them, your job is not to say whether you think he did it or not. Your job is to see whether the state met their burden of proof. Did they show beyond a reasonable doubt that he was guilty? They're testing the hypothesis of not guilty, and saying, do we have enough evidence to reject that? So in the case, I guess I need to go back to the whiteboard. In the case, this particular case, suppose the hypothesis we're testing is that zip code 52001 has the same average income as the rest of the state. It's no different. And I will point out that's, I think Gelman's exactly right about this. That the null hypothesis is almost never of anybody's interest, and it's also never true. There's no way that zip code 52001 has exactly the same income as the rest of the state. It just doesn't. The question is it far enough away, though, to basically be able to say whether it's higher or lower? So the hypothesis we'd set up is that it's really equal. And then the question really amounts to comparing these two numbers, is 80,788, and saying, is it high enough above the 68,446 to reject the hypothesis that we just set up, that if we had all the data, not just 168 households, we had all 5,603 households, is it possible that when we average their household income, it would come out equal to 68,446? How is this test done? Well, you first look at how far away you are from that hypothesis. You know, we're roughly a little more than $12,000 above the mean for the state. What do we have to compare that 12,000 to? Well, we have to compare it to how much variability we would expect when we take a random sample of 168 households. How do we measure that variability? Exactly the way we did in the confidence interval. We say, what is the standard deviation involved in that sample? 29,600. How big is the sample size? 168. So the central limit theorem says take the standard deviation divided by the square root of 168, the sample size. And if you want to be 95% sure, go 2 standard deviations on either side. And that would give you exactly this interval we constructed. It does not contain the 68,000, so we will reject the hypothesis that 80,788, that zip code 52001 really has the same average income as the rest of the state. Clearly, it has a higher average income than the rest of the state. You're going to see hypothesis tests throughout the analyses you do. They're going to pop up all over the place. They're going to be, the results are going to be computed for you. Usually you're going to get a confidence interval with it. I would advise you look at the confidence interval wherever you can, because it's a straightforward statement about what you can find from your sample. 95% sure the true mean is in this interval. The hypothesis test, the sort of double negative logic of it, set up a hypothesis that you're trying to disprove, and see if the evidence is strong enough to disprove it, and if it is, then you reject that hypothesis and state the opposite. If it's not strong enough evidence, you have to throw up your hands and say, I can't say anything because I can't reject the null hypothesis. You certainly, if this interval were a bit wider, you would not want to conclude on the basis of the sample information that it really has the same income as the rest of the state. Your sample, no matter how you look at it, has 80,788. If we make this particular number here larger, we could get this interval to include 68,446, but we still have a sample that has a mean of 80,000, far higher than the rest of the state. So I don't think in any way you want to end up concluding that zip code 52001 has the same income as the rest of the state. So if the interval is wide enough that it includes 68,446, all you would say is, I don't have enough evidence to reject the hypothesis that if I had all the households in 52001, the average income would be the same as the rest of the state. I don't have enough evidence to reject it. I'm not saying that it's right. I'm just saying I don't have enough. Just like the jury in the OJ trial said, the state does not have enough evidence to prove beyond a reasonable doubt that OJ did it. It doesn't mean OJ is innocent. Means OJ was found not guilty. Doesn't mean he didn't do the crime. This is probably the single biggest mistake made by lots of professional statisticians, made in the press all the time. A non-finding is a non-finding, and you cannot turn it into a finding. So when you fail to find evidence, studies of cell phone use over long periods of time, does it lead to brain cancer? A number of these studies have been done. They have failed to find enough evidence to say that heavy use of cell phones leads to brain cancer. The headlines will read, no link found between cell phone use and brain cancer. Depending on how you read it, no link found, you could say it's accurate what they're saying. All they're saying, though, is we failed to find statistically significant evidence. The evidence wasn't strong enough. It doesn't mean that cell phones don't cause brain cancer. It doesn't even mean that we sort of are thinking they don't, or they probably don't. None of that is really true. All it's saying is we have failed to reach the burden of proof beyond a reasonable doubt. In this case, maybe a 95% confidence interval corresponds to a 5% chance of being wrong when we reject the null hypothesis. 5% sounds pretty low, right? But there's nothing magic about it. Even though 5% is the usually adopted standard for statistical analysis, it was actually pulled out of thin air by a statistician 100 years ago, and has kind of become concrete. When you want to publish in journals, you need to find that the probability of being wrong is less than 5%, or they don't publish your articles. There's nothing magic about it, though, and you will see as we go through examples where we try to apply this to real problems, you really don't want this dichotomous thinking of, I need to conclude that something either is different or it's not different. The evidence is always gray. It's never black and white. So the decision should not be black and white. We have a bunch of evidence that we found in our sample. And depending on how sure you need to be and what the risk of making different errors is, you have to reach a conclusion that involves some judgments made about what risk you're willing to take and how sure you want to be. And there's just no way of getting around that. So there's no black and white answer to this. We cannot declare 52001 has higher income than the rest of the state. There's a chance we'll be wrong. We can say we're fairly sure of that because the evidence is pretty strong that 68,446 is a pretty unreasonable level. If this is a truly random sample, that's a pretty unreasonable level for what the average income would be if we had all the 5,603 households in 52001. So we have found something here. I think we can fairly safely say that has higher income than the state average. If the interval had been wider and we were unable to say that, we'd still have a sample that looks higher than the state average. It's just that we would be on much weaker ground and a lot less sure of what we're saying. Might still want to conclude it even if we're less sure. It depends on what we're doing. If we're having to make a business decision about whether to locate a new store in the zip code, because we think it probably has higher income and that's where we're likely to sell more. Well, being wrong, putting a new store in and being wrong could be a pretty costly error. You may have to shut down the store and a bunch of costs that you can't get back. On the other hand, not going into the zip code and putting a store in because you don't think the evidence is strong enough, you miss an opportunity. But depending on what other opportunities you have, that may not be as serious an error. Or it might be that you can't think of anywhere else to open a store, and by bypassing this opportunity, you are really bypassing your opportunity to have a successful business. Every circumstance is different, and you really need to weigh all the evidence. The language of hypothesis testing is extremely confusing, very easy to make mistakes with. Luckily, the computer saves you because it sets these up and gives you the results each time, so you just have to look at what's called the p-value, and we'll see that in the next video, to tell you what the results of the hypothesis test is. But I would always steer you to look at the confidence interval because it's a direct statement saying, based on this sample information, this is the interval that you can rely on, with the caveat that, of course, I'm misspeaking because the interval can only be relied on if it came from repeated sampling. But I don't know what to do with that technicality, so I think it's fine to look at the confidence interval. If it's a 95% confidence interval, say that's the degree to which I can say that the true mean in this case that we're looking for, it lies inside that interval. And underneath this, it's a central limit theorem that's driving the ability to say that. So let me just say qualitatively what the takeaways are, I think, from the central limit theorem, because the further analysis we'll do in the next video involves a whole bunch of different kinds of statistical inference. They have more and more complicated formulas, which I won't be showing you. But the formulas, at their essence, rely on the logic that we just went through. And so the takeaways are that the mean, or it even could be the median or a standard deviation, any kind of summary statistic about data will be less variable than the individual observations. So the mean is more predictable than each of the individual income levels. So means are more predictable, as are any summary data of that is going to be less variable than the individual data. The accuracy will get bigger with the sample size. Random samples are critical. If you don't have a random sample, there isn't much statistical theory can do for you. But if you have a reasonably random sample, the bigger the sample size is, the narrower or less uncertainty you have about what you're trying to infer the value of. The accuracy also will be greater the less individual variability there is. So, the more individual incomes in our sample vary, the more variable our estimate of what the mean will be. Because directly, if this number is made smaller, this interval will get narrower. The larger this number is, the larger, more variable, wider that interval is going to be. The more normally distributed things are, the more they are bell-shaped to begin with, the more you can rely on the central limit theorem. The more strange the distribution looks like, the less reliable that is. Usually you just need a bigger sample to have any confidence in what you found. And the final thing is that random sampling is what allows you to quantify the uncertainty. If you have a random sample, there is going to be some kind of formula, in this case a very simple one for the central limit theorem, but in other cases a more complicated formula. But if you have random sampling, there is a formula that will allow you to quantify the uncertainty about what you found. You have a sample, you're trying to infer something about the population it came from, and the quantification of what you can say from your sample is what is made possible by random sampling and the mathematical theory that underlies it. So in the central limit theorem, it's a relatively clean sort of derivation. We demonstrate by constructing it here just through an example. But in further analyses, the formulas get more and more involved, but they're all derived from the same kind of underlying theory. If you have a random sample, we can look at the behavior of this aspect of the sample, and if you had repeated samples, we can say something fairly precise about what the range of uncertainty is based on what we found. So this is the introductory video on inference, and I will do a lot more variety of inferences in the next recording.